welcome to everybody on my behalf also. So now today's topic is this harmonic filters for renewable energy applications. Now the first slide here, the brief introduction of myself. So my name is Henry Melva, and I'm located in Finland. I work as a lead application engineer for GE Renewable Energy. I have a master's degree on electrical engineering and also a bachelor's degree on electrical power engineering. They are both from Finnish University near where I live here in Tampere, is the city in the central Finland where it is located. I have more than 10 years, almost 15 years at the moment, 15 years experience on reactive power compensation at the moment. I started at 2007 when I graduated from this bachelor degree, and I started with Nokian capacitors, and then now after a few companies that has first Nokian was bought by Arriva T&D, and then it came to Alstom, and then after that GE. So I have been in 4 companies, but still I'm at the same working at the same company that I started. Just has been acquired by other companies in the way. So that was a brief introduction from myself. So now we get to today's agenda, which is like this. This is what I have prepared for you. So we start with the very brief harmonic basics, and then after that we go to defining of parameters of capacitor banks, so what is really required in there. And we go to different capacitor bank types, and the last thing today is the switching transients for these banks. Now, what I have prepared, and this is like for the renewables, this is now on a capacitor bank perspective. We are now trying to get you an idea what is required for the capacitor banks perspective. What is really making sense in there, and what are the main key parameters what we have to know when we design a capacitor bank, and then and that kind of things. This is what I'm trying to tell you with this presentation now today. Okay, let's then start with the harmonic basics here. So first, we have to define what are the harmonics. This is now from the literature what the harmonics are. So they are voltages or currents which have some certain frequency that is multiple of the fundamental frequency. So you can see the equation there below, and then these integer multiples, like from 1, 2, 3, and so on, they are now called harmonics. Then from the bottom left, you can see there's this image. You can see that now there's the most top waveform is the fundamental frequency, and then you have some integer multiples there below, and when you sum these up, you get the waveform what you measure from the network. This is now including the harmonics. There you have the fundamental frequency waveform and also all the harmonics included. And then you get something like this. This is now what we are talking when we talk about harmonics. Then sources of harmonics. Of course, the sources are these nonlinear loads. Everything where your impedance changes the applied voltage, then you get the harmonics in there. You don't get them with linear loads like resistive heaters and lights and so on. But everywhere where you have semiconductors or something like that involved, then you will be facing these harmonic issues. So variable frequency drives, computers, diodes, everything will from these will produce harmonics to your network. Then the impact of harmonics, what these will then cause? They will cause you additional heating and loading, especially the transformers. They will cause additional load to the capacitor banks, what we are now talking. They will increase the voltage stress on capacitors and also the current and voltage stress on the reactors and everything. This is now then those were what are related to capacitor banks. They will increase the peak voltages, so they will cause insulation stress, additional vibration and noise of the telecommunication, and you can have problems with devices measuring zero crossing. You will have, there's a possibility that you will have multiple crossings there. So we'll have failures in operations because of this. And in general, harmonics, they will lead to maloperations, malfunctions, and component failures, and even premature failures, and you will shorten the equipment life with these harmonics. This is what they will cause, and these are the reasons then why we really need to get rid of the harmonics also. Now the basics, you probably know it before this, but just a brief reminder what these are. Then with these harmonic filters, now it's a very typical situation that we don't really know the harmonics beforehand. And if it's a greenfield installation, we really can't go there and make the measurements either. So then we come to this. We get from the standards. Here is now what I'm showing is an IAC standard. From the standards, we can say the maximum compatibility level of harmonics that can be in the network. So this is something that all components in the network must withstand. So if we don't know anything about the harmonics, then we follow this up. So from here we can say that it says that fifth harmonic, there's a 6% harmonic voltage. 7th, it's a 5, 11th, 3.5, and so on. You can see the numbers in here. And then the main thing is also the sentence in the bottom. It says that the total harmonic distortion is 8%. So you choose values from here so that you will get total harmonic distortion 8%. And then this is our best guess if we cannot make any measurements or do simulations or something like that. Then, for example, we can use this dimensioning quite safe for detuned capacitor banks. So if you don't know anything, we can quite safely say that we choose from here, let's say 5% of fifth, or 6% of fifth and 5% of seventh, and then perhaps we typically put like a 0.5% of third also in there, and then that is our spectrum. And then we use that for defining or calculating the detuned capacitor bank. So we use this kind of approach if we don't know anything about the harmonics in the network. And then, of course, we have a similar table for IEEE standard also, IEEE world. So in here, it's just a little bit different compared to IEC world. In here, we have a little bit lower distortion percentage, and also it is different in different voltages here. But the idea is the same behind both of these. So they just define what your equipment must withstand when you put it in the network. So it's in other words, it's allowed to have this kind of distortions, voltage distortions in your network according to the standards. So this is what we follow if we don't get any information. Okay, that was the very brief introduction now on the harmonics. So now we go how we define the parameters of the capacitor bank or the filter in any application. Here I'm just now considering mainly for the renewables, but this will apply to all other applications also. First, this is what we need when we design a capacitor bank. We need to know the rated voltage of the bank. We need to know the frequency. We need to know the reactive power requirement, fundamental frequency, and so on. There are many things that we need here, but it's also the case that we should get as much as possible from this, because if we don't get some value, then we must guess, and then if we make an assumption, then we have to leave some headroom, and then it's not going to be technically, or at least not economically, the most optimum solution. So in other words, it will be expensive. Typically, if we don't get all the information, or we get just few, like you give me the voltage and what kind of power, reactive power you need. If you don't give me anything else, then I have to assume quite a bit of the parameters, and it will lead to probably a little bit expensive design. So now then we go to this defining the parameters. So now the fundamentals of the filtering. So why do we really need the capacitor banks? So we need the banks to produce fundamental frequency reactive power. The amount of the reactive power is defined in the system study. So this is something that you really can't guess. There has to be full system study has to be made so we can define what kind of reactive power is needed. Then basis of the system study comes from the grid code defined by TSO. And then what voltage should the capacitor bank to be connected? The preferred voltage point depends on many criteria, but there are a few key aspects. The compensation power is one, and then voltage also, connection voltage. Another one. Sorry, fundamental frequency compensation power, and then the harmonic content. So these are now really defining everything in here. I would say that with a very low power bank, then it's very typical that you use low voltage, because it would be very expensive to do low power bank on a high voltage. Then what type of bank should be used? So you should it really is something that it's impossible to say without harmonic assessment study. And then again we need a study in here. It's also something that I really can't guess or say beforehand anyhow. So I can only say that if you just need to produce fundamental frequency reactive power, then perhaps a detuned capacitor bank is a good solution there. But if you need filter harmonics, which you typically do in renewables, you have some kind of need for that, then you need to do the harmonic assessment study. And then in that, when you do that, you define what kind of capacitor banks or filters are really needed in there. Then it's really depending now again a lot on the harmonic content, what kind of frequency your harmonics are, and also are you able to handle losses there, or do you want to have the as low losses as possible, and so on. There are many things defining what kind of capacitor banks there should be. We are getting to that on a later stage, what kind of banks there are, and pros and cons on each design or each type of filter. So it's really, if you and then again, if you don't have the harmonics, then shunt capacitor is always cheapest solution. But then you will have some issues. You can have resonances, and you can have all sorts of issues. We will get back to those also later on. Then first here, the reactive power capacity. Grid code always defines the reactive power of the plant. For example, this is now from INSO-E grid code for wind turbines, says something like this. Then these are now things that you have to take into account when you do the system study, where you define what kind of capacitor bank or how much you need reactive power in there. There were two key features that you have to think with capacitor banks. There were reactive power capacity is one thing, and then the other is how you filter harmonics. But these are two different things. First, you have to decide how much reactive power you need, and this now comes from the system study, and this is defined by TSO. You have to have some kind of reactive power reserve in there in your network. It's mandatory. It's really the TSOs, they are requiring you to do so. So you have to have some kind of capacity there. And if you can't, for example, you cannot make all the required reactive power with the wind turbines, then you need capacitors in there. So you will have the reserve, what is required in there. So this is the first aspect in here. This really defines now what is the reactive power needed for the gap. And it comes from the system study. It's something that it's really impossible to define any other way. And another important thing is now the harmonic assessment study then. This will define what kind of filtering you need there. You have a requirements from the grid code in here, the diagrams in the bottom. We start from the left one. So you can see now the darker blue, there is the grid code requirement. This is just one case, this is just for an example here. The grid code requirement is the darker blue curve, and then simulated or measured or whatever is this lighter blue. And you can see that it's now at the lower harmonics, it's much higher than the requirements in the grid code. And now we have to do the harmonic assessment study and define, we will try there what kind of filters, we will change the filter parameters and so on. And when we do the study, we will get to a situation now in the right. So you can see that now all the measured or simulated harmonics, they are below this dark blue line, which means that we are now following the grid code and now we are compliant with that. So this is what we do with harmonic assessment study, and now this really, in this study we define what kind of filters are there. Is it going to be single tuned filter? Do we need two single tuned filter for different frequencies, or do we need some kind of wideband filter or whatever? So this is now why this harmonic assessment study is done, and then what is done in there. So we define the equipment there. Okay, and here's then some concerns that might be interesting to you with this capacitor bank connection voltage versus reactive power. I have seen some things that somebody is asking a capacitor bank, for example, very low power to very high voltage. For example, if you have a wind park and you need, let's say you need 1,000 kilowatts, only 1 megawatt additional reactive power there, and then you might think that, okay, we have here a connection point of 110 kV, so we could use that. That would be the most convenient for us, but it's not really convenient choice to put 1 megawatt capacitor bank into 110 kV voltage. You can see it. I have tried to explain it here. So case is that there is a maximum voltage what the capacitor unit can be. So it depends now on the protection, what is used. If it's a fuseless or internally fused capacitor, is a little bit different. But in here, I've calculated that if you, for example, if you have a 110 kV bank, and we are now using internally fused caps in this because the voltage is something like this, it would be, you would need 5 units in series to get to this 110 kV voltage. This is because they are star connected, so there is only base to ground voltage across the capacitor. So this is the reason why 5 would be enough. So it's a voltage across the capacitors will be 110 kV divided by square root of 3. So this means that the capacitor unit would be something like 100 kilowatts, and the voltage would be more than 12 kilovolts in there. Very unpractical capacitor unit. It would be very expensive to do it like this. So the most economical range in here would be, I would say, something like the power range should be a few hundred kilowatts for each capacitor. If it's not, then it's typically not like an optimal design. So in here, I would say that it would be for 110 kV, it would be something like 18 megawatts would be like the minimum, or something like the minimum optimum power. It would be a little bit less, perhaps 15 megawatts would be still okay, but you can see that this means that 1 megawatt is not okay. So rule of thumb here, low power is very impractical at high voltages, and vice versa here. So this was now what I had here for the defining of these parameters of the capacitor banks here. So then we go to the bank types, because now, because of the harmonic assessment study, what was made there, we can now, and there we define what kind of capacitor bank types we have there, or what we will be using there. So first in here, I have here the list of the possible medium voltage and high voltage capacitor banks what you have in there. So first is the shunt bank, of course, without any reactors, and then you can have tuned filter, double tuned filter, detuned, wideband, or E-type filter. So I will now go all of these, and I have a little bit of more details on each of the types here. First, shunt bank without reactors. So it's the cheap and simple solution here, but now you can have the problem of resonances here with this. So this is not typically something that you can use with these many of the renewable applications. They are not typically these, because you always have the resonance issues. You have a variation of the for this short circuit power, and you will have harmonics there also. So this is everything is now sounding quite bad when you think about as from this shunt bank perspective. In here, the short circuit power, for example, it means that in this diagram at the bottom right, you see there are two curves. There's the red curve, and then you have the black curve. Now, they are for with two different short circuit power for the network. So you can see that the resonance frequency, the network, is now changing when you change the short circuit current or short circuit power of the network. So in this example, you can see that it varies from 8.7 to 11.8. So for example, if you have any 11th harmonic in the network and you just put this capacitor bank there, you will have, with some certain network configuration, you will have a situation where you have the system tuned so, or system is operated so that the resonance frequency is exactly at the 11th harmonic. And this means that when you have the 11th harmonic there, this will amplify it quite a bit with solution. So you will have a resonance with it. So this is not very good solution on this kind of applications. Here are then more about the resonances. So now we have the resonance in here. There are two ways what kind of resonance you can have in there. Typically your network and your transformer and everything, they are inductive. You have the transformer in there and it has the secondary winding which is inductive in there. Now when you add your capacitor there, if you don't have any reactors in front of it, you will have a resonant circuit. Now when you have the connection of the system so that you will have now resonant frequency same as some harmonic in your network, this resonance between the transformer windings and the capacitor will amplify this harmonic quite a bit. So this is why we need something else than this tuned filter network. Then the worst case is this serious resonance in here, because now the harmonic source is somewhere else and it's not the transformer what you have, or not in your network. It can be, for example, in a factory in a next spot or something like that. And then when they are doing their manufacturing there, if it's a factory, they will produce harmonics, and now it's injected there on the higher level. Then you will have your transformer winding and then your capacitor. There's a resonance. They will amplify this harmonic that comes from another source. So this is very tricky to see beforehand if you have this kind of situation. These are typically you see when you start to have problems or you make measurements that you will have. So this is also one thing saying that if you are in danger of having any harmonics in there, then the shunt capacitor bank is not really an option there. And compensation in a network affected by harmonics, this is the typical situation for any renewable application. You need a reactor in there. For example, here we are now put the reactor in series with the capacitor, and it's tuned to 189 Hertz, which is a common tuning frequency. If we have a 50 Hertz fundamental frequency, there is a little bit above the third harmonic in there. So now we are assuming that there are no harmonics below the fifth. So fifth is the first. Now this capacitor bank is tuned so that you can see that it's capacitive below this 189 Hertz and it's inductive above it. So it means that if the first harmonic that we have in the network is the fifth, our capacitor bank is inductive. So it's also inductive. It's also like there's not possibility to be any resonance because the transformer winding is inductive, and now our capacitor bank impedance is also inductive above this 180 or frequency. So inductive capacitor bank and inductive transformer winding, they cannot make any resonance. So this is now then safe to put this kind of capacitor there, and you don't have to worry about the harmonics or worry about the resonances if you put the reactor on top of a capacitor in there. Then the next one, this is the detuned filter. So this is now like a single tuned filter, but it's now tuned off from any specific harmonic. So this is now to avoid resonance problems. So in here, it's very similar. It is the same thing as single tuned filter. We have a reactor and then we have a capacitor in there. It filters some amount of harmonic, mainly only fifth, but little bit seventh and so on, but it's very minor in there. So this is just to produce fundamental frequency reactive power in a network where you have harmonics. So this is not really doing much filtering in there. It does a little bit, but only very little. The dimensioning issues in there, it's very difficult to determine the harmonics in the network typically, because typically when we have an inquiry, there are not given any harmonics to us. So it is difficult. So this is like this. Then we do the dimensioning according to the IEC or IEEE, as I showed earlier in there. Then must be tuned to lower order below the lowest order harmonic occurring in the network. So you have to know something about your network, but it's for example, in renewables, you typically know quite a bit on the harmonics, so it's easy to say what is the lowest order harmonic that you have in your network. And then you tune this detuned bank below that frequency. Then you are safe from resonances. Then if tuned too low order, might absorb, if you have a parallel transformer there, this filter might absorb the inrush current. As you know, the inrush current is typically the second harmonic. So if you tune it too low, close to second, this really starts to affect so that it will absorb the transformer inrush, and this will really, really stress the components, the filter. So you might be in a situation where you burn the filter because of the parallel transformers. So tuning frequency should be low, but not too low. And then it can also cause peak voltage transient if the side step is big compared to the short circuit power. This is something that has to be also defined by simulations, that this will not happen. You will always have some kind of voltage transient, but if you have a very weak network and very high power bank, then you always will have very, very big transients. Then I've had here one calculation example for detuned filter. So first, this is just a tell you how we calculate the filter and what kind of math is behind it. Just a reminder. So this is now example. We have a 10 megavar detuned bank with 10 kilovolts. And then I have put it here 50 hertz as a nominal frequency, and then we use the tuning frequency 189 hertz. The first thing what we must realize is that the capacitor and reactor are connected in series in here, and the phasors, voltage phasors, they are pointing in opposite directions. This means that the reactor will increase the voltage stress of the capacitor. Okay, and this is now also called as a K factor in here. So this K defined as in the first equation here. So you have the frequency and nominal frequency, and then you get the K factor, which is now how much the reactor will increase the capacitor's voltage. As I tried to explain that the phasors are in opposite direction, so voltage of the capacitor is more than the network voltage. Okay, and then now when we know the K factor, we can calculate the capacitance and the inductance values. So we must know now the total reactive power of the bank. Here now the 10 megavars, and then we know the nominal voltage, and we know the nominal frequency, and we know the K factor. So like this, we get that the capacitor is now 296 microfarads. Okay, and the same thing we do with the reactor. We know the tuning frequency in there, and we know the capacitance and so on. And then we get value of 0.396 millihenries. Okay, now we have defined the capacitance and the inductance. Capacitance of the capacitor and inductance of the reactor. And then next, we need to define the current of the reactor. That's the most critical point for reactor, and the voltage rating of the capacitor. Okay, typically we don't get these values, so as it is a detuned filter, so we have to use this IEC or IEEE. I have in this example, I have followed the IEC way. So I have chosen so that the total voltage distortion is around 8%. So we have no scientific, as I have wrote in here, we have no scientific way to divide it into individual harmonics. So use the rule of thumb here. We take the 5% of 7th, 6% of 5th, and then 0.5% of 3rd harmonic. These are equal, quite close now with 8% total harmonics. And then this is the harmonic spectrum that we will use now here. So now we know the harmonic spectrum of the filter, we estimate that this is the maximum what can be in the network. As I said earlier, this is then the maximum from the compatibility level of equipment. So we can say that this is now then the maximum harmonics that you will have in the network. Okay, then now we have all the values, so we can make this kind of table here. So first of all, you can see that we use 1.1 times the fundamental frequency. This now comes as the typically the maximum voltage, maximum continuous voltage is 1.1 times the nominal voltage. This is the reason why I have put it here, the 1.1 times here to the fundamental frequency. Okay, and we get this kind of the capacitor reactance and the inductor reactance in here at these frequencies we have here. I have calculated it, and then total reactance also. So here are then the voltages. This is the face-to-face voltage from third from the right. Then you have the reactor current spec, and then you have the capacitor voltage. Now as the capacitor is So we calculate the voltage for each frequency where we have the harmonics, and then we sum them up arithmetically as this is required in the capacitor standards. We calculate this voltage by arithmetically summing the voltage components in there. So we get 7,488 volts for the capacitor base to ground voltage. And the reactor we get 175 amps RMS current. So the capacitor rated power will be, there's a calculation there, you get need to know the capacitance and the voltage. Now we know the voltage, so on. So it will be 5.214 megawatts per phase. So the total capacitor dimensioning rating will now be 15.65 megawatts, and the rated voltage for the capacitor bank will be 12,970 volts. So this is how we define now the bank. You can see that this is now producing 10 megawatts in 10 kilovolts, but still our rated power of the bank is 1.5 times that, what is the nominal at the moment. Because we have the harmonics. We have to leave room to the bank design because of the harmonics. So this is what the harmonics are now doing. They are increasing the equipment cost in here also. So this is, but it is now then, of course, safe to put to this network. And then if you want to filter more, then it's just this kind of calculation also, but then you just cannot use this voltage percentage anymore, because then, of course, the impedance of the filter will be 0 at the tuning frequency. So if you have any that will be divided by 0, so then the approach cannot be this. Then you have to know what is the harmonic current there. So you have to do simulations, or then you have to do measurement, define that. But this is how we calculate the detuned filter. The brief example of that. Okay. Then the single tuned filter, also called notch filter, depending on what kind of literature you're reading. This is now very same to this detuned filter. Now we are just tuning it into some specific frequency. This has very good filtering characteristics. It's a very simple solution. There are disadvantages. It has higher losses, and each harmonic needs to be filtered by own filter. Then some dimensioning issues or issues when you place this to your network. It is very difficult to determine the harmonics, so measurements for a good simulation model of the network is needed here. Impedance curve can be affected with the filter Q factor, so we can change this a little bit by changing the Q factor. We can change the Q value of the reactor, so we can increase the losses. So by increasing the losses of the reactor, we can decrease the quality factor of the reactor and also quality factor of the filter. It now then quality factor defines the shape of the impedance curve. Okay, lowest order filter. So if you have many filters in the lowest order filter, must be switched on and off. Must be switched on first and off last. So, of course, because if you have lower order harmonics in there, and then you have only higher order filter on, you are in danger of having resonances. So you can, if you have, let's say you have 5th and 7th filter, and you need only one, you have to use the 5th. It's not impossible to use only the 7th filter in there. Then you are in very danger with having resonances. So you always have to use the lowest order. Have 2 filters and you only want to use one, then you have to use lowest order in there. Multiple filters, yes, have to design the lowest order filter, handle the full harmonic spectrum also. Because then again, if you only use one filter, it will be the lowest order and the full harmonic spectrum will still be there. So it has to be able to withstand it. Of course, it will not stress that much the lowest order, the higher frequencies will not invest that much to the lower order filter, but still you have to take it into account. Switching, same as with the detuned filter, if it's tuned very low order, it might absorb the parallel transformer inrush current. So then again, something to also consider. If it's a second filter, which is the case in some applications, you might need a second filter there. So you would fulfill the grid code requirements. Then you have to be very careful if you have transformers connected parallel to the second filter, because it will absorb the inrush current and is in very big danger to burn the filter. That means that dimensioning must be very robust. The filter will survive the parallel transfer. And then this also can cause quite a big voltage transients in there. Okay. Then we can have a double tuned filter. This is now like a two filters combined into one application. This is quite typical in renewables. For example, in wind parks at the moment. This is even with the medium voltage, it's quite typical to use this kind of double tuned filters, because it has a very big advantage. One advantage, it has lower fundamental frequency losses compared to two individual single tuned filters. So this is now this will filter as good as two individual single tuned filter, but you will have lower fundamental frequency losses. This is very important to many renewable operators. So this is the reason why it's increasing in demand of these, even with lower or medium voltage applications. They are nowadays using double tuned filters. There are some dimensioning issues with this. I would say the worst thing in here is that you need very precise information on the network when you put something like this in there. Because now, when you compare it to single tuned filter, you will have additional resonance point. This parallel resonance will be there. You will have series resonances. So these series resonances are the tuning points of the filter, but between them you will have this parallel resonance. If you have harmonics between these tuning points, this can also amplify those harmonics. So you really have to have a very comprehensive system study done if you want to put something like this in the network. So this is something you cannot put like just by guessing the values. You really have to be sure what you are doing when you put something like this. There are some things only. The second reactor in here, the L2 must have a full lightning extent level, so we can use reduced value for reactor L1. So this is making it in some cases it can be a little bit cheaper than this L1 because of this. Then impedance at the resonant frequencies can be tuned with reactor Q factors. Of course, this also we can change the Q factors, play a little bit, and so we can change the shape of the impedance curve by. Then we can affect filtering characteristics. So these are typically used in high voltage or medium voltage if the required total power is small. So for example, in wind parks, it's not typically to have that big requirement. And of course, if you have a big requirement, you can also have an additional detuned bank or something like that there as an addition. But for filtering, this is at the moment at least the demand is increasing for this kind of with renewables. Then with wideband filters, we have two options. This is now the first one, which is the second order high-pass damped filter. So now we have a capacitor and we have a reactor and we have resistor connected in parallel with the reactor. So this is now this now has a white, so by changing the resistor value, we can affect a lot to the impedance curve of the filter. Now, so it means that we can filter with single filter wide band of harmonics. So it means that if you have a harmonic content is in very high range, and you have not too much of the harmonic content, but it's just very wide and it's at the high frequencies, this is the way to go. Because then you can filter with one filter, you can filter the whole spectrum way. So this has a very high fundamental frequency losses, so that it means that it's not practical to have high reactive compensation power with this. Okay, filtering in here, I would say that these are almost all of the things here as I covered when I made the introduction on the last slide. So this is like a very typical, for example, the range is in, let's say, 5 megawatts, and then if it's going to 13th harmonics, that's like a typical approach with these wideband filters. It's not typical to have higher than this power with it. The reason why we can even use these is that we don't even have to use this kind of the resistor value. We can play a little bit. We don't have to use the lowest resistor value, which is now the lowest curve in this picture where you have the impedances. We can use something resistor value with a higher resistor. So we would get something like let's say the purple curve would be okay, because the filter impedances might say it's high at the frequency where you have the harmonics, but also you have to remember that the network impedance increases when the frequency increases. This means that it will still filter quite good the harmonics in there, even if the filter impedance is high. So we can use higher resistor values, means lower fundamental frequency losses, and still it will filter quite good the higher harmonics in there. Okay. Then another C-type filter is this C-type, or wideband filter is the C-type filter. It's a high-pass damp filter. Also can find somewhere this kind of word MSCDN, which is typically, we are referring then to C-type filter. This means mechanically switched capacitor damping network. So this is a more sophisticated name just, but it's a C-type filter. The difference now with this wideband filter is that we have this auxiliary capacitor, C2. Very, very important thing here, because now we are forming resonant circuit with the reactor and with this C2 also. And this is now tuned so that the resonant frequency is at the fundamental frequency. So all the fundamental current will go through this branch where you have series connection of reactor and the C2, as the impedance in this branch is 0 at fundamental frequency. So this is doing the same thing as the wideband filter earlier, but now with the dramatically reduced losses at fundamental frequency. So this is a more smart option just for that. This is now the one typically used with the renewables, as with this the losses are much lower, and typically the losses are something that very important feature with this renewables. So we want to reduce the losses as low as possible, and then this is much more sophisticated solution compared to the wideband filter earlier. The dimensioning issues with this is that now the auxiliary capacitor C2 can have very high capacitance value and very low voltage. This will have issues with the protection of the capacitor. So it might be impossible to make the protection work for the capacitor in certain cases, or something like that. We might have to design the capacitor to be very expensive in order to make the protection work or something like that. And then it can be very tricky to get the protection work with the same settings, C1 and C2. So this is like a typical medium voltage thematic is in here. You can see that we have only one CT now for the protection of the capacitor. So this top capacitors in there, this 1, 2 that are connected, where the resistor is connected parallel with auxiliary capacitor and the reactor. And then we have the main capacitors bottom. It's very typical that we protect them like this, and we have only one CT for the unbalanced protection. And now it can be tricky to get the protection work with this kind of solution. It is typically we can make it work and we can calculate it and we can say it's safe to use this, but it can be tricky. It's just the dimensioning issue that has to be taken into account. And then number of capacitor units must be equal in this. Use this kind of thematic. It has to be equal in both stars in this, for both branches. So you, for example, you cannot have one in parallel in one branch and two in parallel in the other. That will not work. And then the resistor dimensioning, depending on the protection method, split resistor can be needed in here. It is a split resistor because we want to use only one CT. We have to split the resistor in here. And then typically used with lower tuning frequencies and higher voltages, and is very useful for lowest order filtering multiple filters. So as it really, you use it only one filter, this C-type, this will then filter also a little bit the others because it's a wide band filter. So this is very typical for renewables, something like this also. And the double tuned, in some cases, it's increasing the demand with those, but this is like the, I would say, what I have seen and what I have designed these filters. This is perhaps the most typical filter with these wind farms. So this is very, very typical in there. Okay, then the last aspect in here is the switching transients. This is also quite interesting for renewables because the short circuit powers might be that big and so on, so you might have a capacitor banks in there. Here's the circuit that I have used in this simulation. I made a little simulation here. So it is the network short circuit power is a 700 MVA, voltage is 21 kV, and the capacitor bank power is 10 megawatts. Schematic for what I made the simulations is in the right, and this circulated breaker is the one that we are now switching on and off here. So we have a capacitor in there, we have the external network, and we have the breaker. And the first thing here, what you have to remember is the picture now at the bottom left, is that when you switch the capacitor off, you will have a residual voltage in the capacitor. This is now the issue. When you switch it off, the voltage will not go to zero. There will be high voltage, and in some phase it will be almost a peak voltage, at least close to peak voltage when you disengage the capacitor from them. This is the reason why you have the issues here. Now we have to think about this switching transient. Okay, so first we switch a shunt bank with the three-phase circuit breaker. Now it means that all phases are connected simultaneously, so we don't have one-phase breakers that would break each phase with a zero crossing point. So this is not the case now. We are using just a regular circuit breaker here. So one of the phases we always close to maximum transient, and in this case, maximum current transient is approximately 8.0 power unit. Switching time, of course, will slightly affect the transient magnitude, but now in this case, when I have made it, it's around 8 PU. Can be 7 or can be a little bit higher, depending on, again, the exact moment. Which the bank really depends on that. But okay, it's very close to this anyway. So you can see it's quite high. It's 8.0. Now we do with this we do the when we have done the calculations. I've also we can make the impedance curve calculation from the frequency sweep, or from the curve here what we got, the transient, we can divide it with the Fourier analysis, and we will also get the same frequency. So the frequency of the inverse current in here is about 380 Hertz. Okay. Then how we damp this kind of transients? Now there's an easy way for here. So we just add a reactor in front of the capacitor, and it will help and it will damp the transient in here. So in this example, I have put just a detuned reactor, 189 Hertz blocking reactor, which is a 31.7 millihenries. It will damp the transients from 8.0 power units to 4.6 power units. So it will really help. But now, then you have to remember that when you do this, you put the reactor in front of there, it will damp the maximum values, but also it will make the transients last a little bit longer time. Okay. Then the voltage transient, when we switch on the bank with a 3-phase circuit breaker, will cause, of course, now voltage transient. This peak magnitude be affected from the network surge circuit power over the power higher the transient. So high voltage transient can cause problems to equipment. For example, frequency converters or motor drives or something like that, they will trip from over voltage. Many power electronics don't like it if you have this kind of thing. So in this case, the maximum transient voltage is 1.93 pu. That is quite high value. So if you have something like this, it's very likely to have problems with the power electronics in there in your network. So you have to do something with this voltage transient. Again, the same thing when we add the reactor in there, it will reduce the transient. In this case, is reduced to approximately 1 power units, which means that now your power electronics in there, they are not affected switching. So it's now, I would say this value is okay for at least most of the equipment. If there's any problems, it's only with a very few to withstand, in my opinion. So this is the way to go if you have any kind of voltage transients. You need to add inductance there in front of the capacitor, and then it should be taken care with that. Okay, and then this then also very important thing when you have this. It's in a renewable zone anywhere. You have to take it into account that you switch off kind of capacitor bank with a circuit breaker, a circuit breaker. There is this transient recovery voltage in there. So this now the issue is that with this, very difficult to do anything with it. So in this case, what I have made a simulation, but this is now made with the Dig Silent software, and not really meant for this kind of this fast simulations. So now the values can be totally wrong or something like that. But just giving you an idea what to take into account. So don't look at the values; they might be totally wrong because the software is not meant for this fast simulations. But still, we have gotten value that there will be voltage across the transient voltage across the circuit breaker will be 8.5 power units And then this is just something that the circuit breaker should be able to withstand. And if the breaker itself is not able to withstand this, and it's not capable to break the circuit, when we have this kind of transient recovery voltage, there is a possibility for restrike inside the circuit breaker, and then restrike typically destroys the breaker. So you just have to make some kind of this kind of simulation, and then you will define what kind of transient recovery voltage you will have in there, and then you have to choose the circuit breaker so that it will withstand this transient recovery voltage what you have in there. Increasing resistance of the capacitor in theory will reduce the transient, but it's not very practical way because it will losses, so on. So that's not really, that's a theoretical idea there. It's not really something what you can practice much. So you just have to, in here, you just have to choose your circuit breaker so that it will withstand the. Okay, that was the last slide. My presentation. Here is the conclusion. You can, what I've here said for you. So you can study needed for defining the filter parameters. Shunt capacitor and harmonics can cause resonances. Optimum voltage of filters depend on the compensation power. More complex filter requires more detailed information of the fit. Adding inductance series with the capacitor, we dampen the transient. So these were my conclusions, 5 most, at least on my opinion, most important things to remember from this. Okay. Let's see what kind of questions we have here. We have here one saying that what software tools do we use for harmonic simulations of networks, and also that how does the results compare to actual measurements. So I would say that what I use in there, what kind of calculations I make or simulations, I use the Dick silent. So it is probably, at least it's very widely used in this industry for this kind of harmonic studies and harmonic simulations. But for me, for example, I don't really do that much really comprehensive system studies, as it takes quite a bit of time, and my job mainly is making the filter design, so it's not really making simulation. But still, I use that on some typically not that comprehensive studies, but that is used. And how does the results compare to actual measurements? It depends very much on how accurate your model is from the net. It's typically we don't get enough information from the network to make like a very precise modeling or very precise anything. So it depends on this. So I would say it's not. They are not perhaps so good compared to the actual measurements, as we typically don't have enough accurate information on the network when we do the model. We use very simplified models, but that it is what we are not really doing. Or I am not doing that much this kind of full studies for you. But you would need this kind of very comprehensive information. Hope that really answers your question. Okay. What we have then here, then can optimization algorithms help design power filters, and are they any practical? Well, very hard to say. It depends how good your algorithms are, but what I have seen and what I have done, I have really had an idea what kind of filters I would put there. So I would say that it's very typical that guys that are doing this system studies, they know what kind of filters are typically used and how we will get to this kind of result what they are trying to get. So of course you can use algorithms, they will give you some kind of solutions, but it is also possible that you will not get as good and as optimum solution as you would have when you have enough background information experience. So it's like you also need like any rule of thumbs here and what kind of thing. Okay. And there are many questions about the slides. Are they being shared by email? But that's something that I have to get back to you later on that. But I will tell you that it's still something that will be shared to you is the recording. You will afterwards you get to the recording and see again, have some questions raised up to your mind. You'll be getting link for this recording, and then you can see it from there. Okay, then we have here some question about relevant trends and subjects. Somebody is asking that it's really helpful to know the future. So I can tell you what is my view with this. I really cannot say that it's where the industry is going, but my view is that need of this kind of things is increasing at the moment because the headroom in the networks is really used at the moment. So with new installations, all the regulations are more strict, and you have to follow. The emission limits are lower and so on. So you need more filters in there. And also nowadays it's going to this kind of way that the measurement for this is always made by connection points rather than the total amount. For example, if you have multiple wind farms, you cannot use it or calculate it by sum of all of those, but you have to consider connection point of each of your wind farms. So it means that each connection point has its own balance. That's the future with this. So it also means that the amount is the requirements is increasing. Then with some of the modern wind parks, it's also there will be situations where no fundamental frequency compensation is needed. So they will only need filtering. This means that you have to use some kind of active solution. This is a STATCOM or something like that. Or the other approach is that you will have passive filter. What I was now talking to you, passive filter. So for example, C-type filter, and then you put shunt reactor in parallel to the filter and compensate the fundamental frequency power of the filter by the shunt reactor. So it means that you will have an equipment or gadget which has a zero reactive power output to the system, but it will still filter the harmonics. Okay, so this is one also thing that is increasing. And because of this, as I told you, the measurement point issue, sizes of the equipment, I would say they are not going, at least they are not going to bigger at the moment. They are probably going smaller capacitor banks in renewables. So those are the things that I am seeing when I am now dealing with these inquiries. This is the things that gotten into my mind. Okay. And we have here a question about one question that there is a specific question about 33 kV system. If you have where you have a requirement of compensation power of 20 to 35 megawatts in steps of 5 megawatts, which they are asking how it can be realized in open rack construction, multi-stage switching. The metal enclosed construction needs a substantially bigger civil footprint and it's not economically viable option. Okay, so it can be, I would say, if you have a, let's say you have this 35, or let's say you have 30 megawatts, when the range was 20 to 35 megawatts. If you have a 30 megawatt requirement, you want to have it into steps of 5 megawatts, I would divide it myself into one bank of 15 megawatts, one bank of 10 megawatts, and then one bank of 5 megawatts. So with these 3 banks, you would get 5 steps, 5 megawatt, 10 megawatt, 15, 20, 25, and 30 megawatt. I would do it like that. And the physical size for this kind of one bank is, I would say, roughly something like from 3 times 5 meters to 3 times 7 meters if it's a space bank. Something like that is the footprint what is required. Okay. Then we have here a question, considering involved cost, are the active filters an economical and affordable option? Okay. It really depends now much about what is the requirement in there. The active filters, they are always very much more pricey compared to these passive. They are very expensive, but if you have no other option than that, then have no other option. I would say that if you have any other option, then you would prefer the passive filters in there. But there are cases where you just need something faster that we can provide. For example, the reconnection time for this kind of passive filter, if you switch a capacitor bank off, and then the time that you can switch it back on, there is typically something like 10 minutes there. You have to wait 10 minutes that the residual voltage in the capacitor units themselves will drop so that you can connect the capacitor bank off. So this is an issue. In some cases, you might need faster response. For example, your requirement is that you have to be able to reconnect the banks in very fast, let's say 1 minute or even less. Even some cases might be seconds. Then active filters are then your only choice. We can reduce the time, reconnection time with passive filters also into quite short time, but still we are not able to be as fast as with active. So if there are requirements that require active filters, then that is typically the only way to go. Then these passive solutions will not go. Okay, then there's a question: is there a rule of thumb for KVR / KV when evaluating the practicality in there? I would say that the most the best option, or at least the cheapest, economically best option, is always to use as high KVR rating for the unit as. But then again, the voltage also it depends a little bit on the bank connection. But if there is no let's say barriers or anything coming from the bank connection or bank design, then I would also say that it's quite the economically best option is to use also typically quite high units. Again, it might be with medium voltage, not the case, because you would have a little bit cheaper on by playing a little bit from the bank connection. For example, you can connect 2 caps in series per phase or 3, then and change the number of parallel units and so on. But if you have a high voltage capacitor bank, always the cheapest bank will be when you have highest KVR rating possible and the highest voltage. And then there are not really, in our way, we will tell send an inquiry to us. We will tell you if it's, there's something strange in the numbers that are there. But I would say it's really, there are no other limits than it's practical. Most practical is the highest voltage and the highest reactive power possible for the capacitor. Okay. There's a question why transmission lines have parallel and series resonance where everything is connected in parallel. So this is just there were two ways how the resonances are coming there, or how we have a series resonance. It means that it comes from somewhere else, the section of the harmonics. If we have a parallel resonance, then the means that the harmonics are coming somewhere that is in parallel gap bank. And if it's series, then you have the series connection between, so you have transformers and upper voltage level and again transformer and so on. Just the name of the resonance called series and parallel. There. Okay. And there's a question about complex filter design. So you need to know more about the system. How do you find out more about the system or validate models with local measurements? What type of measurements? This is the thing that very good question in here. That if we have a very complex filter, for example, we have a double tuned filter, or we have a C-type filter, or anything more complex things, or many single tuned filters in there connected in the same system. We have to know a lot because we have the resonance issues in there and so on. This is very difficult to say where you get it. You have to have very precise model of the network. This is something that you typically don't have. Very unlikely that you will have enough accurate model for example, the heating network, that you can make a system study where you can say that everything will be covered. Then again, there will be very many scenarios in your network when you make the studies. As you know, there are very many connections in the network. For example, the loading is changing, and then you might have a different connections in the network and everything. So everything like this affects the network impedance, and then it means that eventually you will have very many simulation points, and then you just make the simulations, and then you get the worst from those, and then this is then what you have to deal with. So you have to just make the simulations so with all the parameters you can imagine that they can happen, and then you have to verify that the filters will work on every one of those scenarios. Or then you can make measurements, but then if you make measurements, you have to then make long time measurements, of course, because some things in network, they might happen only once in a week or once in a month or something like that, and it can even this one episode can be very bad to your equipment for your system. So if you make measurements, you always make long time measurements, so not just for 1 hour or something like that. You have to be very long time, to make the measurements. Also, you have to be on a right place to make them. You can leave the equipment there for a long time, and this is the way. There are not really an easy way to do it. It's always quite difficult to do that. Okay, then we have here a question about the filter design basics. So what is really the design basics. So I would say that, as I told you earlier, first you determine the reactive power needed by filtering, filter types and quantity, what kind of they are. Then determine the connection voltage based on availability and choices and the needed compensation power. And then if you have a very small compensation power requirement, let's say up to 450 kilowatts, this can also be made with low voltage capacitors. But in here, feeder for these capacitors, low voltage capacitors, is the limiting factor because the fuses have to be very big. So it's not really practical to have more than 450 kilowatts with low voltage. Everything beyond that typically has to be medium voltage. Then medium voltage, the most common place to put the filters in here, and then I said earlier, it's 1 megawatt power upwards for 33 kV, and if you have a lower power than that, then you have to use lower voltage than 33 kV, which is, I would say, quite typical for wind farms. That, like from inquiries that I have had, it's very typical to have this 33 kilovolt voltage, nominal voltage in there. Okay, then we have okay, I will still okay. And there's one question that is your product scalable? As our projects vary from few megawatts to up to 100 megawatts renewables. Also, good question, and all capacitor banks are scalable. So these capacitor units, they are like building blocks. So if the power increases, we just increase the number of capacitor units in there. We connect more of them in parallel to obtain more compensation power. Okay, so it is still you have to, as I have tried to point out here, that it is very difficult to do these, let's say, 33 kV banks with a very low power. So I would say that from let's say somewhere 1 to 2 megawatts, that's the smallest power what we can typically with 33 kilovolt range for these renewables, from my perspective at least. So anything smaller than that, it's not really that practical. There is no practical upper limit, so anything can be. Okay, then we have here the following question for the what I tried to say about the studies is that, so assuming you don't have detailed model and of the system, you just test the configuration and works up a trial and error. When you do the system study and simulations, you always typically, if you do it for wind farm, you have your wind farm, you have very precise information from that. So you can do your study based on that, on your equipment. Then the TSO will give you some impedance range. They will give you something, but impedance sector, where the impedance of the system will be. So you will, with this information, will lead to very big number of individual simulations. But yes, you can make the design or make the study with those, but that's all we can do. We will have an impedance sector from the TSO, and then we will have this information from what you have from your network, and then when you combine them, you make enough quantity of simulations from different network impedance, then you will get the worst case there, which you will use for your finding the parameters for your component. Hope it now clarifies. So it's not really a trial and error, and not really a guessing. It's like a we will have some information, and then means that we will make quite a bit of simulations, many high number of simulations there with many some points in there, some like a impedance with different network impedances. We make numerous simulations, and by that we define the worst case and be used. Okay, I think that we are now getting end of the time, so I think that was the last question here, and I will now hand it back to Holly. Okay, thank you all on my behalf.
Thank you so much, Henry, and thank you everyone for attending. We look forward to seeing you again at our next event. This concludes today's webinar. Have a wonderful day.